capacity of a DMC is the supremum of all achievable rates. So, if you don't know what supremum means, it's approximately the same as max. It does have, there's some subtlety between supremum and maximum, but it's helpful to think of it in terms of max. Okay. Those are our 9 definitions. Now, the last thing I'm going to do in this class is I'm going to state the channel coding theorem and its converse, and then next class we will set about proving it in earnest. The noisy channel coding theorem. States the following. Let C, the capacity, be equal to max, or P of X, of mutual information. Then, all rates are less than C are achievable. By the way, this is where supremum comes in. So if I put in R less than or equal to C, that's max. This is the subtlety, is that that's supremum. So in other words, I need not be able to achieve C. I can achieve anything up to C, and it's still valid. I need not necessarily be able to achieve C. So all rates R less than C are achievable. That is in the sense of definition 8. So in other words, there exists a sequence of codes for every rate R less than C, such that the maximum, the worst probability of error of any message transmitted using that code goes to 0. The converse. The converse says this. Any sequence of 2 to the nr n codes with lambda n going to 0 as n goes to infinity must have r less than or equal to c. In other words, no rate greater than C is achievable. So in other words, C is fundamental. C tells us the maximum rate at which I can transmit reliably in a channel. There do exist codes so that I can transmit reliably up to C, but not beyond. Anywhere beyond C, I cannot achieve arbitrarily low probability of error. There's no sequence of codes that does this.
Is that a strict inequality in the first and...
Here, this is strict inequality.
Yeah, there isn't.
This one is not. In practice, it doesn't matter, but yeah, this one is strict and this one is not. In other words, it's helpful to think of it this way. Rates less than C, achievable. Rates greater than C, unachievable. Rates equal to C, I don't suppose it matters very much. Okay, this is really Shannon's channel coding theorem. This is Shannon's big accomplishment, is showing that there exist non-zero rates for which reliable communication is possible. Now it's important to notice all of the arguments that we're going to present of this feature, that n goes to infinity. In other words, these are only really achievable with really, really, really long code word lengths. In other words, if you have very short messages, these kinds of things don't apply. These kinds of arguments don't apply. Especially, let's say you're only trying to communicate one bit, then these kinds of things don't apply. There are different avenues you can go in information theory. There's a field called zero error information theory, which actually has absolutely nothing to do with these kinds of probabilistic arguments, but just tries specifically to avoid errors. If you only have one bit to send, it also doesn't really make sense to have a code. You might want to think about detection and estimation. It's more of a detection and estimation problem. Information theory does have things to say about that as well, but we're not going to talk about them. I think I will leave it there for today. So what I would advise you to do between now and Thursday is keep the definitions in mind, because we will be using them when we talk about the proof of both the theorem and its converse. So it would probably be a good idea between now and Thursday to just, or at least just before Thursday's class, read back over those definitions and make sure they're fresh in your mind.